Okay, we're doing 3D today. In the classroom, something you can't see at home, we have a 3D X, Y, and Z axis set up so that kids can be able to try to see these vectors in 3D. For right now, I've drawn one on the board that's just in 2D. It's got an X and a Y axis. No, it doesn't. It's got a what? You remember from what I said before? I and J, very good. This is the I and this is the J. And then the thing that would be coming straight out at you, in fact, so perfectly straight you couldn't even see it. Coming straight out at you, that would be the Z axis. No, it's not. It's the what? K. We use I, J, and K in this unit. Okay, now this vector AD, one of the hardest things for kids to get is that if I move it here, you know what it's still called? AD. And it's exactly the same as it was before. Now that doesn't seem possible. Like, wait a minute, Mr. Server, that's definitely in a different place than this. And here's the questions you have to answer because it's always about this. Does it have the same direction? Yeah. How do I know? Because it still moves over this way 5 and up that way 5. That means the direction's the same. And what do you think the magnitude is? It's the length of it. Do you get its length would be, well, it's the 5, 5 what? Triangle. 5 root 2, very good. This would be 5 root 2 long, whether it's here or here. It's got the same magnitude either way. So it's got the same direction and the same magnitude. How about now? Still the same. How about now? Yeah, still the same. Okay, so moral of the story, if a vector has moved around, then it hasn't actually changed. And I know that's really hard to like imagine in your head, but that's the same as this, which is the same as this, which is the same as that. Oops, there. Okay, so then what do you do with vectors? You typically add them or subtract them when you're just learning. So let me show you a nice simple one. Let's say I have this little vector here, and I want to add it to this little vector here. What on earth am I going to do to add these? Like lay them right on top of each other? Nope. But let's say I put this one here. And let's say I called it 2, 1. Do you get what I'm doing there? The blue one, or so the red one is 2, 1. Another way to write that, 2I direction plus 1 in the J direction. But 2, 1 is so much cleaner and easier to write. We usually use what's called column form. So that red one, 2, 1. Does that make sense to you? If I moved it here, isn't it still 2, 1? Yes, it is, because it moves over 2 and up 1. Get the idea? And then what's its magnitude? Its magnitude is how long it is. If it's over 2 and up 1, it's the square root of, can you do it in your head? Square root of 5. It's the 2 squared and the 1 squared. Remember how we always do these with the square root of the other two things added after you square them? So 2 squared is 4, 1 squared is 1, square root of 5. That's the magnitude of the little red vector. No, I just erased him. Can't do that. I'll just move him back and then erase. There we go. Now, why did I move him there? Because it's much easier to see he's 2, 1 when you put him there than if I have him like over here. That's a lot harder to tell he's 2, 1. It's really hard to tell if I put it like that. Not even on any lattice points. Okay, so there's 2 comma, whoa, undo. Okay, and then I'm going to move this one over, and I'm adding them together. Does anybody want to take a shot at what the resulting vector is? Yes. Think about that again. How far over, how far up? Try again. I know you know that you're doing, but you said it slightly wrong. The resulting vector would be this pink one, and it'd be over what and up what? Try one more time. I can get you off the hot seat if you want. All right, pass it on. What do you think, sir? 4. Yes, because the pink one, if you just look at the pink one, try not to look at the red or the green. Do you get that the pink one goes over 3 and up 4? The answer is 3, 4. The red one was 1 or 2, 1. I want to move it in position. Oh, that's too messy. The red one was 2, 1. The green one was 1. Over 1 and up 3. Do you get how I got the 1, 3? Now look what happens when you take the red one plus the green one. You get how you get the black one? Because the 2 plus the 1 makes the 3. And the 1 plus the 3 makes the 4. Does that make sense to you? And the 3, 4 thing is like this. Over 3, up 4. And the pink one is over 3 and up 4. That's how you add vectors. Now, how do you subtract vectors? You put them the other way. What do you mean the other way? All right, I'll show you. Get the pink thing out of there. We just got the green one and the red one. What if I said the red one minus the green one? Anybody got a theory on what I'm going to do? What do you think, sir? So what do you mean by opposite vector? I'm going to make the opposite vector blue. Do you mean like... How about this? Now, you might have meant like over here somewhere, but do you get that that's the same exact thing as this? Because if I move it, remember, I can move it here, here, here. It's the same vector. It's going the same direction, same magnitude. The red one minus the green one gives me the black one. The red one plus the green one, hold on, just move this out of here. The red one plus the green one was this answer. The red one minus the green one is, it's better if you just move this down here, but realize that its arrow has changed directions. Turns into this one. That's subtracting 2 vectors. All right, I'm going to give you one. I want you to try and see what you think the answer is. Make a nice, simple little red vector. You have color capabilities on your iPad. Make a little red vector that does that. Does it even matter exactly where I graphed it? Nope. As long as it goes 1 to the right and up 2. I do strongly recommend take a second, drop in a Post-it or something that's got graph paper, because this whole thing, you want to keep things lined up. Like if you just kind of sketch them, you really have to guess at what the answers are. Take a second and get graph paper. It's worth it. All right, then I'm going to have you add that to this vector. Now for me, I'd move them because I know that they're exactly the same if I move them around. Red one plus black one gives me blue one, which would be 4, 3. 4i plus 3j, aka 4, 3 in column form. Yay, you've learned how to add vectors. You just lined up their tip and their tail. This blue one is the one that results, so it's called the resultant. The blue one is called the resultant. Now, if you understood that one, try figuring out what the red one minus the black one would be. Red one minus the black one. Right away, I'm going to draw the black one backwards. Same length though. And then I'm going to put it here. And take the blue one out of there because I don't have the blue one. It was the red one minus the black one. And then the final answer would be this blue one. Raise your hand if you had that one right. Okay, some of you are catching on. Now, Do you remember that problem that had 3D in it back a while ago? There were some kids that were like, oh, I can't do the 3D. Honestly, I had kids with straight A's that ended up getting like an F on that test. And it's because some people just have a really hard time with 3D. Hate to break it to you, that's not even 3D, that's 2D. Okay, we're going to get into 3D. I have it set up in the room so you can see it better. But if you're one of those people that's challenged in that, then you need to take time to figure this stuff out. Draw good pictures. Okay. Yes. The blue's answer vector would be like this. -2, 1. And if I wrote the red vector, it would have been 1, 2. If I'd have written the black vector, I would have said it was over 3 and up 1. Like how far over did it go? How far up did it go? You know, like that. So guess what happens when I take the red one minus that one? What do you think you get? 1 minus 3, -2. 2 minus 1, 1. It works. Question? Okay. All right, so a typical homework question for tonight. 2 things. They want to make sure you get that they have direction and magnitude. So if I just tell you that I weigh 234 pounds, it's true. So here's the question. Is that a vector? What it has magnitude, what doesn't it have? Direction. Now, my 234 pounds is going to collide into John at 1 mile per hour. Boom. There. That had direction and magnitude. In fact, it had 2 kinds of magnitude, believe it or not. It had my speed and it had my weight. And then you guys can do all kinds of cool physics stuff with that, which gives you the idea that me throwing this tennis ball at you at 5 miles an hour, ready? That didn't even hurt his hand a bit. Okay, but if that was a baseball, which weighs a lot more, and I threw it 90 miles an hour, it would have hurt. Why? Because the amount of magnitude was quite different. And that makes a total of, what's that called? Force equals mass. Can anybody finish that one? Times acceleration. Very good. I'm pausing the video. Okay. All right, back with you. So, here is a typical question. Does this have direction and magnitude? Yeah, because I know what direction it's going. And I know its magnitude by its length. Do you get that this and this are going in the same direction, but they have different what's? Magnitudes. All right. Let's say my bank balance, I'm not going to tell you that number. Okay, let's say that you have a number. Does that have direction and magnitude? No. How about I move a chair from back there to up here? Do we have a direction at least? And couldn't the magnitude be construed as how far it is from there to here? Yeah. Could it be the weight of the chair? Yeah, there's a lot of things that the magnitude could be. So I got direction for sure, and I could figure out some magnitude for it. So if you got direction and you got magnitude, then you got a what? A vector. Okay, so the first part of the homework is just identifying what's a vector and what's not. If it's not a vector, it's called a scalar. If it just has magnitude, you could weigh it on a scale, right? It's a scalar. All right, so the next part of it is, if I drew a picture, notice no backdrop of graph paper. Here's my question. What if I added up AB plus BB, no, that doesn't make sense, BC plus CD I shouldn't change colors at that point. I should stick with the black and go with that's D. Is that equal to dA? It's close. It's not equal to dA. How about this? If I add up AB plus BC, it would be equal to AC. AB plus BC, you get how that equal to AC? So, how about this? I'll tell you the answer. The answer is this blue vector, because that's the resultant. That's what you get when you put them all tip to tail. I think you get it if I give you two of them. Do you get that those two add up to this black one? Okay. What if I make three of them? That plus this. Do you get that that adds up to that? All right. Is that exactly the same as that? No. Opposite magnitude or opposite direction? Direction, okay. That's opposite direction as it should be. So if I call this A, and this B, and this C, and this D, then it's not, the answer is not DA. The answer would be AD. Because it should have the arrow on the other end. That's the only thing wrong with this thing. It's going the wrong direction. The answer is like this one. I'll make it with a different color yet. The answer is like that one, except it have an arrow on this end. Okay. One more thing that freaks people out with these kind of drawings. Let's say I had this, and it doesn't even have, nope, that's not the right drawing. That was a trapezoid. What I want is a parallelogram. A, B, C, D. BC is the same exact vector as AD is. Because I know you can tell I didn't draw it perfectly because of how it's not lining up nice. But that and that are the same direction and they're the same length. If this is really a parallelogram, these have to be, by definition, the same length and the same direction. So then that makes them the same vector. Do you get that this also another set of vectors with AB is the same as, be careful of what the order you say it in. AB is the same as DC. Yeah, this is the same as that one. I don't even want to show you because it won't line up perfectly. But anyway, okay, you can get the idea. They're the same thing. AB is equal to DC. In vector world, they're going the same direction, and they're the same magnitude or length. So they're the same thing. Okay, so then tell me, what's the same thing as CB? DA. Good. This is a tricky one. What's the same thing as BD? Don't say it. Write it down. What's the same as BD? And don't say CA, because he's not. And don't say AC, because he's not. What's BD the same as? It's kind of a trick question. Who's got an answer they think is right? Hannah. BD is not exactly the same as DB, but it's really close. What's the difference between them? Think. Different direction, and therefore, do you know how you could get the direction piece out of a vector? Never told. Yep, you could make it a scalar. How could you do that? How could we say that BD all of a sudden has no direction? You haven't seen the symbology for this yet, but I think it's the last thing I have to teach you. Yes? Nope. Yes? Nope. Good guess. Yes? Add a domain. I like the idea, and it's kind of like that, but that's not it. If the direction isn't important. All of a sudden, I don't want to strip out the direction. I don't know which way it's going. Absolute value of it. Okay, so now you've been taught everything in theory. So let's see if you actually caught it all. I asked you before, what's the same as BD? And you could say the opposite of D. B, that would have been safe to say. Negative means opposite of, right? If I said, here's 7, and then I go like this, isn't that the opposite of 7? Yeah, negative can be construed as opposite. So, how about this? Would this have been an okay answer? What's the blue vector? You could have said AB plus BC plus CD. And you don't know this yet, but this is the symbol for a vector. It's a different symbol than you've ever seen before. You might think, oh, we had those in geometry. It's like a ray. No, that had a full arrow on top. Do you note I'm only doing one of the little like feathers or one of the little like points on the arrow? It's not the feather end, that's the point end. So this thing, that's called vector. Now you've really learned everything you need to know for today. So let's actually look at the homework because I need to spend a little bit of time in the lab today still. The new lab that we haven't finished yet, and some people I think is really complicated, and it's actually really not. I know you think it is, and until I get it, until somebody shows you, it could be confusing, but if you're thinking it's super hard, it's not. You're just not understanding the question then. So anyway, let's look at the homework for tonight. I'm going to pause for a second while you pull that up. Find this page in your homework. This is 19.1, chapter 19, last chapter of the year. Yeah? I know, we have 3 weeks left. What do you think the last week is? Well, what is the last week is actually finals week. Remember, we have a whole week of finals. Okay, it's not a full week, but it's close. Okay, so like I think you have Monday is a review day, and then Tuesday, Wednesday, Thursday. So it's one day of review, and then that's finals week. So then that leaves us 2 weeks left. And one of those is a short week. You know what I'm talking about? Because we got Memorial in there. So we don't have that much time left, is all I'm trying to say. I know. Technically, I think we have 19 school days left, of which I'm going to say 4 are basically that last week. That leaves us like 15 school days left, which is about 3 weeks of this unit. But it involves a lab, and bottom line, we have a fairly big chapter, a test on it, and a lab, and that's what's left. So this is the last melon, last chapter. Okay, number 1, a classroom chair is moved from the front to the back. Woohoo! Does it have direction? And the distance it moved, wouldn't that be the magnitude? Could it be the weight of the chair too? Yep, but this definitely can be a vector. Number 2, the balance in a bank account. Scalar, good. Number 3, electric current passing through. Okay, does electric current have ways to measure it, like how strong it is and stuff? Yep, so that's got magnitude. Does it have direction? Yeah, it's going through this tube. So the electricity is moving in a direction, and so it's got direction and magnitude. So that's not a scalar, it's a vector. This one, number 4, I could see arguments whether or not this is or is not a vector. And just think it over for yourself and then go see what the key says and get your own opinion. I could make an argument for both. That it is a vector or that it isn't. It's kind of a tricky one. Number 5, an aircraft starts its takeoff run. Is it just a snapshot, like a picture of the aircraft? Then that wouldn't be a magnitude and direction, so it wouldn't be. But if it's actually moving, it starts its takeoff run, it's like moving down the runway, then yeah. All right, last thing, I want to make sure you get this in your head about vectors. Remember, their length matters. So this and this could be both going the same exact direction, trying to make them go the same direction. What you can't see at home if you're watching the videos, I'm holding up a yardstick and then a little box that looks kind of like a yardstick, except it's only like a foot. And they're going the same direction, but they have different magnitudes, right? And remember that also I can move it around. As long as I keep pointing the same direction, it's the same vector, no matter where I move it. So the preferable place to move it is so its tail end is right at 0, 0, because it's easier to see how far over and up it's moved. Last thought, A vector isn't just a dot. You know, all our other units, we were just describing a dot. Polar was just saying, here's where the dot is. You go this way and that way, and that's where the dot is. This is actually the arrow is the vector. It's not just a dot. It's the arrow going to the dot. And there's really no dot. It's just the arrow. And last thought, it's like a little man running on the ruler. Little tiny guy, but this tall. And he's running on the ruler. Why? Because two vectors can cross each other, and yet the vectors might not collide. What I mean by that is, if I'm holding them like this, do you get if the little man started at the end of the ruler and started running, that they wouldn't actually hit each other? They would go through the same spot, but they wouldn't be there at the same time. You get what I'm saying? So a vector isn't just an arrow or like a ruler. It's like a ruler, except a little guy running on the ruler. So that when your two vectors cross, they not only have to cross at the same spot, they'd have to have their little man that's running on the ruler get there at the same exact time. So if I made them both exactly 1 foot from the end, then they would cross and collide. The little man that's running on the ruler would hit each other. Okay, you'll get to that at the end of the unit. I just wanted to give you the big picture here on vectors today, and I've done that. So now we got to get it down into the actual homework. We are going to do these problems, except skipping D and E. I think if you get the other ones earlier than that, they're just kind of overkill. So when they throw an absolute value, remember that strips out the direction. That just means magnitude of. Because if the absolute value, you don't care if it's the opposite of it or itself, and therefore you don't care what direction it goes. All right, so let's just do one of these. Do you see that I have drawn A, B on here in red? And then I drew BC on there in green. And then I drew AC, which is what the answer to part A is. It's AC. I drew that on there in blue. Your drawing is not graded. You just have to figure out what the answer is. So the answer for A is AC. Now, one thing that I wish was on here but isn't, is that a vector, when you're drawing them, would have these little lines that have sound like an arrow on the end, but it's only one side of the arrow. So they kind of look like that. I'm not going to grade you on that. Don't worry. Right now, on the test, you'll have to know that. But this is day one, and it's not on the worksheet. So you know. All right, and then there's one question right there that tries to start you thinking about using like, oh, I know an angle and a side, and so therefore I can use trig. Remember this deal? If you can make a right triangle and you know one side and one angle, sine of 20, blah, 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 that kind of stuff. All right, and then since they asked for absolute value of it, that means it means the magnitude, which means how long it is, not what direction it's going. How long is that? So it's almost like they're trying to get you to figure out how long that is. Or is it the other way? All right, good enough. Giving you enough hints. And that's all of the new stuff. Now, stay tuned. I'm going to give you more help on the lab. So you may recall, this is a complete different topic now. This is talking about the lab, which is about complex numbers. Do you remember that if you graphed them, oops, we've got to keep the angles the same. I'm going to make the 3/3 roots. That's the 3/3 roots, 12-minute warning, so we should be in the homework, but we already are, so that's good. Okay, so extra few minutes of help on the lab. First of all, this is a drawing of the 3/3 roots of 1. You know how long that is? 1. How long is this? 1. And what's this angle in here? You might say, well, it's 360 divided by 3. Yeah, that's true, which would be 120. But wait, that only works for this exact situation. What if we say we could generalize that angle to be? 2 pi, which is the same as 360, right? Divided by n, which is how many roots you have. I think some of you have thought that this is way harder than it is, but it's not that hard. How long is the black line? Well, you'd use the law of what? Of cosines. And you know A, don't you? I'm not going to write the law of cosines. If you are not willing to go look that up, then you don't get it. Okay, the law of cosines. I know A. How long is A? 1. If we're only going to do the roots of 1, 1 is how long these are always going to be. How long is B? 1, so you stick that in the formula. How long is C? That's what we're trying to figure out. This third side here, that's the distance. That's C. And then what's the angle? Because you need cosine of, in the formula, a squared plus b squared, blah, blah, blah. We need the angle. This is the angle. Cosine of that angle. And you've got your general form for it. Once you get your general form, it's super easy to answer the other questions. There are other questions in the lab. They say, like, if you're confused on what this means, do you get that really means this? Oh, wait a minute, plus. No, I don't want it to be negative. Hold on. C to the third minus 1 equals 0. Do you get that means this? And then that means you're going to have to take the third root. And that's the point. You're doing the third root of 1. So what if they change this to a 4? Then this would be a 4. And then what would you need to do for both sides? Fourth root. So really, when they give you one of these, they're asking you for the third root or the fourth root. And then they only ask you to do the third root and the fourth root and the fifth root. And then you're trying to find the distance. How far is it from here to here? And we just gave you a formula that you could use for that. So I hope that helps. Some of you may not figure out the lab. If that's not the end of the world, it's just a homework assignment like this time, like it has been almost every time in the past. And you do get 2 thrown out at the end. And if you just can't figure this out, I think you're going to be disappointed when you see the answer. Super simple. I'm just trying to solve the distance formula for C. All right, not distance formula. Sorry. What's that other formula? Cosines. Okay, so that's my hint on that. And the last thing I'm going to do today is hand back your tests, your most recent test. I know some of you haven't taken it yet. If that's you, you should be planning on coming in either after school. You won't be able to finish it today after school, but I could get you done with the first probably 2 pages. And then I could give you the rest of it in class. Or Wednesday during Mass, or Thursday before school. All of those are good days to come in and take this test. I will be here in this room in room 1430. And that's all I got for you for today.